Right now, hundreds of miles above your head, there's a satellite just threading a microscopic needle through the vacuum of space.
Yeah, going roughly 17,000 miles an hour, too.
Exactly. And if it drifts by even a fraction of a degree, it either burns up in the atmosphere or just gets completely lost to the void.
Right.
And the only thing keeping that multi-billion-dollar piece of hardware exactly where it needs to be, it's a differential equation. So welcome to the deep dive. Today we are looking at this stack of notes labeled Day 25 from Chapter 9, Sections 9.1 to 9.3.
Which sounds super intimidating.
It really does. I mean, differential equations, or DEs, it sounds like intense math jargon,
Oh,
but I promise you do not need a math degree for this.
no, not at all.
Our mission today is to demystify these structural definitions. We want to reveal how they act as the secret blueprint for, like, everything moving in our world, from orbiting satellites to the physics of your favorite video games. Okay, let's unpack this. Because beneath what looked like just a wall of math, there's this beautifully elegant machinery.
Well, it's the machinery of causality itself. I mean,
Right.
differential equations aren't just abstract numbers floating on a whiteboard somewhere. They are the literal mathematical language of change over time and space. So whenever you have a physical system in the real world that is changing, this is how we capture it.
Like what kind of systems?
Whether that's heat dissipating from a car engine or a biological population growing or, a rocket accelerating. A differential equation is how we capture the exact, uncompromising rules of that change. They basically connect an unknown function with its derivatives.
And before we can build rocket ships, we kind of have to understand the basic grammar of this language, right?
Exactly. Just like sentence structure tells you if you're reading a question or a command, mathematical structure tells an engineer exactly what physical problem they're dealing with. And the two most fundamental pieces of that grammar are order and degree.
Yeah, let's start with order, because it seems to dictate the fundamental complexity of the system.
It does.
The rule in the notes is that the order of a differential equation is simply the highest derivative present anywhere in that equation. So, for example, the notes give us this equation, the second derivative of y with respect to x, plus 3 times the first derivative plus 2y equals 0.
Right, a classic example.
Because the highest derivative in there is that second derivative, the d squared y part. This is a second order ordinary differential equation, or ODE.
Precisely. You just scan the equation for the highest derivative. If there's a third derivative somewhere in there, that's the ceiling. So it's a third order equation.
Okay, that makes sense.
It gives you an immediate sense of the system's depth. But then we introduce the degree, which measures something slightly different and honestly slightly trickier.
Yeah, the degree is defined as the power, or the exponent, applied to that highest order derivative. But only, and this is a massive caveat, only if the equation can be expressed as a standard polynomial.
This is where people constantly get tripped up. The polynomial requirement is absolute.
Right, so the notes contrast two examples. First, you take that second derivative, put it in parentheses, and cube it. So it's raised to the power of 3 plus the first derivative equals sine of x.
Right.
In that case, the highest derivative is the second one, so it's order 2. And it's raised to the power of 3, so the degree is 3. That's a standard polynomial structure.
Yeah.
But then the notes throw in a literal trick question.
Ah, yes, the transcendental trap.
Yeah, it's the first derivative of y with respect to x plus the cosine of the first derivative equals 0. Wait, so math just throws in literal trick questions. Because the derivative is wrapped inside a cosine function, it can't be expressed as a polynomial. So the degree is just undefined.
It is undefined, yeah. Because a transcendental function, like a cosine or a logarithm, actually represents an infinite series of terms if you were to expand it mathematically.
Oh, wow.
You can't just point to a single highest power when the expansion literally goes on forever. So the rigid rules of polynomial degrees just collapse.
It's kind of like, okay, think about counting the gears on a car. If you drive a traditional gas car, your grammar relies on distinct steps, right? Gear 1, Gear 2, Gear 3, that is your mechanical complexity, which is like the order. And the horsepower applied to that highest gear is like the degree.
I like where this is going.
But then you get an electric vehicle. It uses a continuously variable system. You know it has power, you know it has speed, but the rigid grammar of gears just doesn't apply to how that specific motor operates. The mechanism is just completely different.
What's fascinating here is how these simple structural rules tell you exactly what kind of physical problem you are dealing with. By identifying the order and seeing if the degree is defined or undefined, An engineer instantly understands the nature of the
Right,
system.
they know what tools to use.
Exactly. They know if it's going to oscillate, if it's going to decay, or if they need to approach it from a totally different mathematical angle.
Which naturally brings us to the solutions themselves. Because once you classify the equation and you do all that incredibly complex calculus, you don't just get a single number.
No, not at all.
You get either a general solution or a particular solution. And this is where the notes really emphasize that a solution is like an entire universe of possibilities.
Yeah, when you find the general solution to a DE, you haven't found a single answer. You've essentially found a family of curves.
A family of curves, right?
Structurally, a general solution contains as many arbitrary independent constants as the order of the equation. So if you just solved a second-order ODE, your solution will have two arbitrary constants, usually written as C1 and C2.
Because integrating inherently leaves you with an unknown constant.
Exactly. And because those constants can theoretically be literally any number, the general solution describes the general rule of how a system behaves, but without any specific reality locked in.
So to put this in normal terms for you listening, think of the general solution as a customizable video game avatar.
Oh, that's a good way to look at it.
Right. Like when you boot up a new RPG, you get this basic template. It has the structural rules of a human, 2 arms, 2 legs, but it's a blank slate. There are infinite possibilities of what that character could be.
Yeah, that's your family of curves.
Exactly. And the particular solution is what happens when you spend like 3 hours choosing the exact hair color, the stat distribution, the armor, and then you finally hit save. You've locked in the exact values. That's your boundary conditions locking it in.
That transition from the template to the saved game is driven entirely by those boundary conditions, or initial conditions. You can't find a particular solution without knowing the exact state of the system at a specific moment.
Which seems super abstract, but we actually do this intuitively all the time, don't we?
Oh, every day. Anytime you predict something in your daily life, you're doing this. Take a hot cup of coffee cooling down on your desk. The general solution to that system is Newton's law of cooling. It's the absolute rule that hot things get colder over time based on the temperature difference with the room. That applies to your coffee, a hot piece of iron, or even a dying star.
But I don't really care about the dying star. I just want to know when I can drink my coffee without burning my mouth.
Exactly. So if you know your office is exactly 68 degrees, and your coffee was poured at exactly 190 degrees at time equals 0, those are your initial conditions.
Ah, I see.
You take that universal rule of physics, apply your specific boundary conditions, and the math spits out the particular solution. It proves your exact cup of coffee will be lukewarm in, say, exactly 12 minutes.
That is so cool. It's the journey from the universal blueprint to the exact house you live in.
Beautifully put.
Armed with those definitions, general and particular solutions, let's transition into how engineers actually wield these tools in the physical world, because the notes dive into 2 specific engineering domains, aerospace and electronics.
Aerospace is arguably the most rigorous proving ground for ODEs. I mean, we're talking orbital mechanics here. They use them to model trajectory, thrust, and atmospheric drag.
Right, and the notes specifically call out Newton's law of universal gravitation.
Yeah, which is mathematically expressed as a second-order ODE. It's basically mass times the second derivative of the position vector with respect to time equals the negative gravitational constant times the masses divided by the distance cubed.
It's a lot of math, but essentially is balancing the massive pull of the Earth against the acceleration of the satellite.
Exactly. And when an engineer solves that second-order ODE, the general solution gives them all the possible orbital conics.
Like the shapes of the orbit.
Right. It proves mathematically that the path has to be an ellipse, a parabola, or a hyperbola. But to actually fly the satellite, you need the exact flight path.
You need the particular solution.
Yes, so they plug in the exact launch velocity and altitude at engine cutoff. Those boundary conditions collapse the infinite possibilities into one singular trajectory.
That makes total sense for something massive like a rocket. But then the notes pivot to electronics, specifically circuit analysis. And this completely blew my mind.
RLC circuits, yeah.
Yeah. Resistor, inductor, capacitor circuits, they are entirely modeled using ODEs for voltage and current. The equation in the notes is basically inductance times the second derivative of current plus resistance times the first derivative plus 1 over capacitance times the current equals 0.
Notice the structure there.
That's exactly it. The structural order dictates the complexity. An inductor resists changes in current flow, kind of like how mass resists a change in velocity.
Right, it's electrical inertia.
And a resistor is like friction. And a capacitor stores and releases energy like a sprint. So one capacitor plus one inductor inherently equals a second-order differential equation.
And finding the particular solution tells the engineer exactly how the current will oscillate and decay the millisecond a specific voltage switch is flipped.
But wait, think about what this means for a second. The structure of the math for a multi-ton rocket orbiting the Earth and a tiny microchip circuit flipping a switch.
Yes.
It is virtually identical.
It is.
You're literally just swapping out gravity for electricity.
If we connect this to the bigger picture, that continuity is why differential equations are so profound. They act as the universal source code for reality.
Oh,
They don't care about the physical medium. They don't care if it's rocket fuel or copper wire. They only care about the mathematical relationship between the rates of change.
The universal source code of reality. Okay, well, here's where it gets really interesting. If DEs are the source code of reality, how do we get computers to simulate that reality without just totally breaking?
That is the million-dollar question in computational physics.
Right, because we're shifting from continuous physical engineering to discrete digital simulation, like building the matrix.
Yeah, game engines and physics simulators update object states frame by frame. But there's a fundamental problem. Computers do not naturally understand continuous flow.
Because they can't calculate an infinite number of points on a curve, right?
Exactly. The math says velocity is the derivative of position with respect to time. An engineer can draw a perfect continuous curve for that on paper. But a processor? It's computationally impossible, especially with 100 rigid bodies colliding in a video game at once.
So how do they fake it? How do you simulate continuous time?
They rely on numerical methods like Euler or Runge-Kutta. Instead of solving for one perfect analytical curve, the engine chops time into tiny, manageable intervals.
The notes call this delta t, right?
Yes, delta t, the time step. The engine looks at an object and says, I know your position and velocity right now, so for the next tiny fraction of a second, I'm going to assume you travel in a perfectly straight line.
Oh, so it just makes a highly educated straight line guess for the next frame.
Exactly. It calculates a momentary particular solution continuously, 60 frames a second, stitching together tiny straight lines to render realistic collisions or, like, cloth tearing.
But if it's just guessing with straight lines, doesn't that introduce errors?
Huge errors. Floating point math on computers causes microscopic rounding errors. Over thousands of calculations, those errors compound. The simulation drifts, and suddenly your rigid body falls through the floor of the video game.
Which perfectly explains the practical coding requirement in the Day 25 notes. There's a hands-on task to write a standalone Python function to verify if a test solution to an ODE is actually valid.
Right, but you don't use standard Python math for it.
You use the SIMPy library. Wait, so basically, we are using Python and SIMPy to build a robot that double-checks our incredibly complex math homework automatically.
That is exactly what you're doing. SIMPy handles symbolic algebra. It treats variables as pure symbols, avoiding those rounding errors entirely.
Oh, so it preserves the perfect continuous math.
Yes, and building this as a standalone script gives you what we call notebook readiness. Modularity is crucial. Modern engineering isn't just about knowing the math by hand. It's about building reusable, automated workflows to test these chaotic systems safely before you ever build them.
So what does this all mean? We started with the grammar of math order, degree, and the trap of transcendental functions.
Right.
We looked at how general and particular solutions build the physical world, from orbital mechanics to RLC circuits, and finally we saw how we have to use frame-by-frame coding in SIMPy to actually simulate and verify this stuff in a virtual world.
This raises an important question, though.
Okay, lay it on me.
Think about the contrast here. We know that our entire physical reality, the continuous trajectory of planets, the flow of electrons, is perfectly modeled by these continuous differential equations.
Yeah, the math is flawless.
But our absolute best computer simulations, no matter how powerful, are forced to artificially chop that reality into tiny, discrete, frame-by-frame time steps that delta just to process it.
Right. They can't handle true continuity.
So if the only way an intelligence can simulate a working universe is by rendering it one microscopic frame at a time, are we entirely sure our own universe isn't just rendering reality one microscopic frame at a time?
Oh man, wow. Are we just living in a universal delta T? That is a wild thought to leave off on. Something for you to definitely mull over the next time you drop your coffee or play a video game. Thank you so much for joining us on this deep dive. We'll catch you on the next one.